Okay, welcome to lesson 4 of waves. Task list for this presentation is number 1, complete and mark the remember questions. Number 2, go through the model slides. You need to be able to draw the diagram of reflection and explain what is happening to the wave. Number 3, complete example questions on the try slides. Number 4, complete the questions on the apply slides. And number 5, complete the assessment for this lesson and make sure that you have submitted it. Okay, let's now start the lesson. So, the first thing that we need to do is we need to make sure that we can fill in these gaps. So write down the information you have here and fill in the gaps as you go. The words are at the bottom of the screen here, okay, hiding quietly behind the black box at this moment in time. There we go. So stop the presentation and complete this, and then we'll go through and mark it. Welcome back. So let's mark the presentation. So a wave transfers energy without the movement of matter. In other words, the particles will stay where they are. They'll move up and down as the wave passes, or they'll move backwards and forwards as the wave passes, but they stay in their own location. They don't move with the wave. In a transverse wave, the particles' vibrations are perpendicular to the direction of the wave travel. Frequency is equal to the number of waves produced by a source in 1 second. This period is equal to the reciprocal of the frequency. The speed of the wave in meters per second is equal to its wavelength in meters multiplied by its frequency. I'm sorry, some of these have jumped down a little bit, but you can still see them okay. Make sure that you've marked them, okay? All right. Okay, let's now move on to the next slide. So this is information that you need about reflection. So reflection is the change in direction of waves at the boundary between two different media. Now we've seen this word before. This just means stuff. This just means a substance of some sort. So that the waves return into the medium which it originated. In other words, if you've got a wave, say a light ray, coming down here, and it hits this mirror here, it will be bounced back out into the medium that it's come from. Okay, into the media that it's come from, into that substance where it came from. So if you had a torch here, where my little red dot is at the moment, it would be shining down onto the mirror and it would come out back into the media that it's come from. And the mirror wouldn't allow anything to pass through it, unlike in refraction. An example of a good reflector of light is the plane mirror, the mirror with a flat surface. So here is your plane mirror. These are known as plane mirrors. Okay, sorry for the cough. Right, so the image is in the mirror. Now, when you look into a mirror normally, you don't just see a ray bouncing in and out. You see an image in the mirror, usually of yourself. So, when you look into a mirror, what you will see is, you will see your face. All right. Now, interestingly, the distance between you and the mirror is the same distance between the mirror and the image, which is very weird. Okay, so here you've got an object here. That distance between there and there is the same as that between there and there. So it appears to be in the mirror, but in fact it's not there. It's imaginary. This one's imaginary. The rays never get to that point. Okay, and that's why it's a dotted line. So the image appears to be the same distance behind the mirror as the real object is in front of it. Okay, this is because the brain thinks that the light travels in straight lines without changing direction. The image is called virtual. In other words, a virtual image is something that doesn't exist. Because the light rays show as a dotted line, which is here, you can see the dotted line here, never really go there because they actually get bounced back and go up to the real image. So here is the real image. The ray comes down here, bounce, and goes up there. So your eye is imagining that the image is here. But the important thing you've got to realize here is that the distance between this image and the mirror is the same as between the mirror and the object. Okay, this one, the image, doesn't exist. It's just virtual. In other words, it's just an imaginary thing that your brain's basically seeing. And this one is the real image, real object. Okay, let's move on then. Okay, now we're going to have a look at reflection in a plane mirror. So here we have a plane mirror, and this is usually the symbol for a plane mirror. So a dark line and then a little hatching behind it. So this is our normal. We've had this one from refraction. So the normal is that imaginary line that is at right angles or perpendicular to the boundary, which is this bit here. Okay, so to the surface at right angles to the boundary of the surface, and it's where this point here will be where the ray actually strikes the boundary. There we go. So this is the incident ray. Now an incident ray is the ray that's coming in, and the way you represent that is by drawing a line and an arrow showing it going towards, in this case, a mirror. Alright, here is our reflected ray. And we know that's a reflected ray because it's moving away from the mirror, from that normal point there, and it has an arrow to show you that direction. Now, you have two angles, and it's always measured from here, which is the incident ray, to here, which will give you the angle of incidence, and between here and here, which gives you the angle of reflection. Now the interesting thing about these two angles is that they should be the same. And the law of reflection, 1. The angle of incidence equals the angle of reflection. Okay. Ooh. Just going to scroll back one slide. Ooh, here we go. There we go. So that is the important bit that you need to know. That yellow box here, even though I whizzed on to the next slide, is an important bit that you need to know. That bit there, and I suggest that you pause the video, make sure that you've written that down and that you have this diagram as a reference. Okay, this is quite a useful diagram, and it sometimes comes up in exams that you need to label these kind of things. But this here, the angle of incidence equals the angle of reflection, is the main thing for reflection. If you don't take anything away from this lesson other than the information in this yellow box and this diagram, okay, you've got it sorted. Okay, so where is the image in a plane mirror? So we have an image, okay, that we're going to form with this light bulb. We have a plane mirror, okay. So when my black box eventually disappears again. Wait for it. There we go. We've got our eye, all right, looking at this light bulb. All right. Now, if we look at the image that light bulb will form in our mirror, okay, you can see that the distance between the mirror and the virtual image, in other words, the imaginary one, the one that's not really there, is the same distance behind the mirror as the real object is in front of the mirror. And all you need to remember is that that distance there is the same as that one there. And you can actually see that because if you look at yourself in a mirror and you move away from the mirror, the image in the mirror will actually move back as well. So let's just make sure we got the information from the slide. So here, the image in the mirror looks the same as the object, but is laterally inverted back to front. Ooh. So what does that mean? Okay, so let's have a look, see if we've got some information on that then. Okay, the image forms is right way, but it's a virtual image, does not really exist. We said that earlier. So we need to find out about this lateral inversion. Okay, dotted lines show the construction of the virtual image. So here's the lines, it's coming in up to there. Okay, still don't know about this lateral inverted or back to front. Ooh, hang on a minute, let's have a look at this. So here we've got an ambulance. All right, so there's a normal view from the front. Same view seen in the rear view mirror of a car. Now what do you notice about the writing on the front of the front of the ambulance here and the front of the ambulance here? Okay, yeah, it's round the other way. And that's what you need to be aware of, is that's lateral inversion. Okay, so it's been turned around. Wait for my black box to disappear again. There we go. The word ambulance is laterally inverted, so that it reads correctly when seen in a driving mirror. So for instance, if someone's driving a car down the road and the ambulance comes up behind them, okay, they'll know that it's an ambulance. Okay, so let's have a look at what we've got here. Nearly all the light that is incident on a mirror is reflected. Some other surfaces either transmit or absorb light. So if we remember the refraction lesson from last lesson, we know that the light can be transmitted. But if you get the angle just right, some of that light will be refracted and some of it will be reflected. The medium which transmits light allows light to pass through it. We've just said that. And the medium absorbs light, basically allows light to pass through it a bit, but doesn't allow it to come out again. So it just absorbs it. So it takes that energy into itself. Light colors are very good reflectors of light. Dark colors are very good absorbers of light. Okay. All waves are affected as they travel from one medium to another. That's interesting. All waves. So sound waves will be, and light waves will be, and water waves will be, and all parts of the electromagnetic spectrum. Remember, the electromagnetic spectrum is basically different wavelengths, including visible light, and radio waves, and gamma rays, and ultraviolet, and all that lot. Okay, so here's a diagram you may wish to stop the video for. So you've got the incident ray coming in, some of it's being reflected, some of it's being transmitted. Now, here is a little practical that you could try at home. You need a light box of some sort. I would suggest that you use your mobile phone. If you cut a small slot in a piece of paper and put in front of it, or card or something, put in front of it, you may need to adjust the distance of the slot from the mobile phone light, so your torch light on the bag, and then you just need a mirror. And you can actually practice, see whether it actually the angles, sorry, of incidence and the angle of refraction are the same. So when you do your little practical, write down your angle of incidence and write down your angle of reflection. Okay, have a go at plotting that against each other and see what you get for that. Okay, if you need a ruler, sorry, if you need a protractor, not a ruler, here is one for you. There is a copy of this as a separate document that you can print out. Okay, the red line is merely showing you where your mirror needs to be. So that red line here is showing you where your mirror should be sat. And what I would suggest is that that line there, that 90-degree line there, is where your normal should be. And you want to be getting your incident ray to strike the mirror right below there. You may wish to extend that line down. And I would start off, say, at 20 degrees, and then 30 degrees, and 40 degrees, and 50 degrees, and see what happens. See where does it go. All right. Okay, complete the question. So write down the law of reflection. Okay, we've already stated that. The angle of incidence equals the angle of reflection. And number 2, explain how you see the image in the mirror. That one's going to be a bit more tricky. You may need to refer to the earlier slides. Okay, but have a go at that. That's basically showing you how an image is shown in the mirror. Don't forget it's a virtual image, and that remember to explain about virtual lateral inversion. Okay. All right, the last thing that you've got to do is complete the assessment for this lesson.